So in this question, we have to determine the values of z for which the complex number given by z minus 2 divided by z plus 2 is purely imaginary. So let us begin by assuming that our complex number is given by z1, which is equals to z minus 2 divided by z plus 2. Now we're going to use the fact that if a complex number z is purely imaginary, if it is purely imaginary, then we say that the complex number z is always equals to the negative time of its conjugate. So let us use this fact. So we'll have to find out the value of the conjugate of z1, which will be equals to simply z minus 2 conjugate divided by z plus 2 conjugate, which is equals to z conjugate minus 2 conjugate, 2 being a real number, so it will be simply 2. And similarly for the denominator, we have z conjugate plus 2. So we know for the z1 is purely imaginary, it is given, so we consider the equation that z1 must be equals to the negative times of the conjugate of z1. So let us substitute the value. So we have z minus 2 divided by z plus 2 is equals to negative times z bar minus 2 divided by z bar plus 2. We can arrange this and we can multiply the negative 1 on the right hand side with the numerator, and that will give us 2 minus z bar. So we arrange accordingly the denominator. The terms in our denominator will become 2 plus z bar. Now we're going to cross multiply it, so we'll have z minus 2 multiplied to 2 plus z bar is equals to 2 minus z bar multiplied to z plus 2. So let us find out. So we'll have z multiplied to 2 plus z is multiplied to 2 plus z bar minus 2 is multiplied to 2 plus z bar, and this value is equals to 2 multiplied to z plus 2 minus z bar multiplied to z plus 2. So this gives us z times 2 is 2z plus z times z bar will give us the absolute value of z squared minus 2 times 2 is 4 minus 2 times z bar, and this value is going to be equals to 2 times z, which is 2z, plus 2 times 2, which is 4, minus z bar times z is the absolute value of z squared minus 2 times of z bar. Now we can cancel out the like terms from the left hand side and the right hand side. So we have 2z on both the left hand side and the right hand side, so they cancel out, and so will negative 2z bar. So that gets cancelled out, and it leaves us with absolute value of z square on the left hand side, and we take the negative 4 to the right hand side and add it to the 4, so that gives us 8. And we bring the negative z squared mod of z squared from the right hand side to the left hand side, so we'll have 2 terms on the left hand side. So this finally gives us the absolute value of z squared is equals to 4, which gives us that the absolute value of z is equals to 2. So we're taking the square root on both sides, the z being the absolute value, so we're considering only the positive value of z. So here the complex number z, when it is chosen in such a way that if the absolute value is equals to 2, then the given complex number z1 is going to be purely imaginary. In this question, we have a complex number z given by x plus iy. Then we have to solve the complex equation z square equals to the conjugate of z. So let us begin by substituting the value of z into our given equation. So we have x plus iy whole squared is equals to x plus iy over bar. So let's expand x plus iy whole squared using the identity a plus b whole squared. So that should give us x squared plus 2 times x times iy plus iy squared equals to the conjugate of x plus iy, which will be simply x minus I times y. This will be equals to x squared plus I times 2xy plus I squared y squared equals to x minus I times y. So we're going to combine the first term and the third term, since I squared is -1. So that would make I squared as negative y squared. So we have x squared minus y squared plus I times 2xy equals to x minus I times y. So now we're going to equate the real part and the imaginary part. So the real part of the left hand side of the complex number is x squared minus y squared, and the real part of the complex number on the right hand side is equals to x. So this gives us the first part of the equation. Then we have 2xy is equals to -y. So this is the imaginary part. Equating them gives us this particular equation. So from here we have 2xy plus y is equals to 0. We can factor out y from both the two terms, so that leaves us with 2x plus 1 equals to 0. So we have two values, y is equals to 0 or 2x plus 1 equals to 0, which gives us the value of x as minus half. Now we're going to use this value to determine the value of the remaining x and y's. So let us do that. So let's use for y equals to 0. Let us use the first equation. We have x squared minus 0 squared equals to x. So that gives us x squared equals to x. We have x squared minus of x equals to 0. Factoring out x, that gives us x times x minus 1 equals to 0. So we have x equals to 0 or x is equals to 1. So from here we have found out two values. So y equals to 0 implies x equals to 0 or an x equals to 1. So from here we have the complex number z, which is x plus iy, will be 0 plus I times 0. So this is the first. So let's call it z1. z2 will be the second complex number, where x is 1 and y is 0. So these are the two values. Let's go for the other one. So we have x equals to half. So for x equals to -half, so we have -half squared minus y squared is equals to -half. So let us solve for this. So we have -half squared will be positive 1/4 plus half equals to y squared. So y squared is equals to 1/4 plus 2/4, which gives us 3/4. And taking the square root on both sides, we get plus y value to be equals to plus or minus square root of 3/2. So we have two values. So for x equals to -half, this gives us two values of y. One will be positive square root of 3/2, and the other one is negative square root of 3/2. So we have the third complex number, which will be negative half plus I times root 3 over 2, and the fourth one will be negative half minus I times root 3 over 2. So these are the four complex number. So these are the first two and the remaining two. So in this question we have a complex equation given by the absolute value of z squared minus 1 is equals to mod z squared plus 1. We have to prove that the complex number z is purely imaginary. So let us begin by assuming that the value of z to be equals to a plus I times b, and substitute this value into a given equation. So we have a plus ib whole squared minus 1 is equals to the mod of a plus ib squared plus 1. So we're going to expand a plus ib whole squared using the identity a plus b squared. So that would give us a squared plus 2 times a times ib plus I squared b squared minus 1. And the absolute value of a plus ib will be the square root of a squared plus b squared whole squared plus 1. Then we combine the real parts, so we have a squared. Now I squared b squared will become negative b squared since I squared is negative 1, and we have minus 1. So this will be the real part plus I times 2ab will be the imaginary part. So square root of a squared plus b squared whole squared would give us a squared plus b squared, and we have the plus 1. So now let's take the absolute value of this particular complex number. So we have a squared minus b squared minus 1 whole squared plus 2ab whole squared, and this value is equals to a squared plus b squared plus 1. Now we're going to square both sides, so that will give us a squared minus b squared minus 1 whole squared plus 4a squared b squared is equals to a squared plus b squared plus 1 whole squared. Now let us combine and let us rearrange the terms. So we have a squared plus b squared plus 1 whole squared minus, so we're bringing we're subtracting a squared minus b squared minus 1 whole squared from a squared plus b squared plus 1 whole squared, which will be equals to 4a squared b squared. So I've arranged the terms in this particular fashion so that I can use the identity that a squared minus b squared equals to a minus b times a plus b. So let us do that. So this will give us a squared plus b squared plus 1 minus a squared plus b squared plus 1 multiplied to a squared plus b squared plus 1 plus a squared minus b squared minus 1, which will be equals to 4a squared b squared. A squared and negative a squared cancels out, and we have b squared, negative b squared, positive 1 and negative 1 cancels out. So that leaves us with 2b squared plus 2 multiplied by 2a squared equals to 4a squared b squared. So let's take 2 as the common factor, which leaves us with b squared plus 1, and we already have a 2. So we can rewrite this as 2 times a squared, which is equals to 4a squared b squared, dividing both sides by 4. So we finally have a squared times b squared plus 1 equals to a squared times b squared. So we have a squared b squared plus a squared equals to a squared b squared. So we have a squared b squared cancelled out from both the sides, which gives us a squared equals to 0, or you can say that a is equals to 0. So we started out with the complex number z is equals to a plus ib. So since our value of a is equals to 0, so that gives us 0 plus I times b, which is a purely imaginary number. So that proves that our given complex number z is purely imaginary. How many solutions does the equation z squared plus the absolute value of z squared equals to 0 have? So let us do that by assuming that our complex number z is given by a plus I times b, and we're going to substitute this value into a given complex equation. So we have a plus ib whole squared plus the absolute value of a plus ib squared is equals to 0. We're expanding, we get a squared plus 2 times a times ib plus I squared b squared plus the square root of a squared plus b squared whole squared is equals to 0. So that gives us a squared plus I times 2ab minus b squared, since I squared is -1, plus a squared plus b squared equals to 0. Now we can cancel out b squared and minus b squared. Combining a squared plus a squared will give us twice of a squared plus I times 2ab is equals to 0, which implies taking 2a as the common factor. So we have a plus ib equals to 0. So we can have either 2a is equals to 0 or a plus ib is equals to 0. However, we're going to reject this particular solution because this is going to be trivial, because we know that this gives us z equals to be 0, and we know that 0 squared plus absolute value of 0 squared is always going to be 0. So this is a trivial solution, so we're not going to consider this. However, when we solve for a, we get a is equals to 0. So that gives us z to be equals to 0 plus I times b. So that means this is a purely imaginary number. Now depending on the value of p, so we can have different types of z. As b, so we'll write as b belongs to the set of real numbers, and there are an infinite number of real numbers. So we have z has infinite solutions. Let us go to the next question. So we are given a complex equation 1 plus I times z is equals to 1 minus I times the conjugate of z. So using this equation, we have to show that the complex number z is equals to negative I times its conjugate. So let us do that. So we have 1 plus I times z is equals to 1 minus I times the conjugate of z. So we can rewrite it as z is equals to 1 minus I divided by 1 plus I whole multiplied by z conjugate. Now what we're going to do, we're going to multiply the numerator and the denominator by the conjugate of the denominator, which is 1 minus I. So we have 1 plus I times 1 minus I in the denominator and 1 minus I whole squared in the numerator. So expanding the numerator, we have 1 minus twice of I plus I squared divided by 1 squared minus I squared times Z conjugate. So we have 1 minus 2I minus 1 divided by 1 plus 1 times Z conjugate. So let's next part. So we have Z equals to negative 2I over 2 multiplied by Z conjugate. So 2 and 2 cancels out, so that leaves us with Z equals to negative I times Z conjugate. So here's the proof. Let's move on to the next question. So in this question we have to determine the value of K for using the given complex equation. So let us begin from the left hand side. We're going to work with the left hand side. So we have the absolute value of 1 minus Z1 bar times Z2 squared. So that can be rewritten as 1 minus Z1 bar times Z2 multiplied by 1 minus Z1 bar times Z2 conjugate minus Z1 minus Z2 multiplied by its conjugate, which is Z1 minus Z2 bar. This will become 1 minus Z1 bar times Z2 multiplied to 1 minus Z1 bar times Z2 over bar minus Z1 minus Z2 multiplied to Z1 bar minus Z2 bar, which is equals to 1 minus Z1 bar times Z2 multiplied to 1 minus Z1 times Z2 bar minus Z1 minus Z2 multiplied to Z1 bar minus Z2 bar. So let us use the FOIL method. So the first multiplication will be 1 minus Z1 times Z2 bar minus Z1 bar times Z2 plus Z1 times Z1 bar times Z2 times Z2 bar minus Z1 times Z1 bar minus Z1 times Z2 bar minus Z1 bar times Z2 plus Z2 times Z2 bar. We have now 1 minus Z1 times Z2 bar minus Z1 bar times Z2 plus mod of Z1 squared times mod of Z2 squared minus mod of Z1 squared plus Z1 times Z2 bar plus Z1 bar times Z2 minus mod of Z2 squared. So here we can cancel out Z1 times Z2 bar, as the both additive inverses of each other are available. Similarly, this one cancels out with this one, and we are left with 1 minus absolute value of Z1 squared minus the absolute value of Z2 squared plus absolute value of Z1 squared times absolute value of Z2 squared. So we're going to combine it. So this gives us 1 minus Z1 absolute value of Z1 squared. We're going to factor out Z2, so that gives us 1 minus absolute value of Z1 squared, which will be equals to 1 minus the absolute value of Z1 squared multiplied to the 1 minus absolute value of Z2 squared. Now this value is equals to K times, so let's rewrite it. So on the right hand side we have k times 1 minus the absolute value of z1 squared multiplied to 1 minus the absolute value of z2 squared. So equating both sides, we get the value of k to be equals to 1, since the left hand side is equals to the right hand side. This is the answer. Let's move on to the next question. So here in this question, we are given that 1 plus I divided by 1 plus 2 squared times I multiplied to 1 plus 3 squared times I divided by 1 plus 4 squared times I all the way up to 1 plus 2n minus 1 squared times I divided by 1 plus 2n whole squared times I is equals to a plus ib divided by c plus id. And using this equation, we have to prove that 2 over 17 times 82 over 257 all the way up to 1 plus 2n minus 1 raised to the power of 4 divided by 1 plus 2n raised to the power of 4 is equals to a squared plus b squared divided by c squared plus d squared. So in order to solve this question, what we're going to do, we're going to take the absolute value on both sides. Now we know from the property of absolute value that if we have the product of two complex number and we take its absolute value, then this is equals to the product of the absolute values. So we can rewrite it as, so we apply the property, so this should give us the product of each of the moduli. So the modulus of 1 plus I will be simply square root of 1 squared plus 1 squared divided by the square root of 1 squared plus 2 squared squared, which will be 2 raised to the power of 4, multiplied by 1 plus 1 squared plus 3 squared whole squared, which will be 3 raised to the power of 4, divided by square root of 1 squared plus 4 squared squared is 4 raised to the power of 4, all the way up to the square root of 1 squared plus 2n minus 1 squared will give us to the power of 4 divided by 1 squared plus 2n raised to the power of 4, which is equals to the square root of a squared plus b squared divided by the square root of c squared plus d squared. Now we're going to take the square on both sides. So we're going to square both sides, and that should give us the final result. So we have 1 squared plus 1 squared, so the square will move away. So we have 1 squared plus 1 squared equals to 2 divided by 1 plus 2 raised to the power of 4. 2 raised to the power of 4 is 16, and 16 plus 1 gives us 17, times 3 raised to the power of 4 is 81. 81 plus 1 gives us 82, and solving the denominator gives us 257, all the way up to 1 plus 2n minus 1 raised to the power of 4 divided by 1 plus 2n raised to the power of 4 is equals to a squared plus b squared divided by c squared plus d squared.